Hi, welcome to this video. In this video, I will explain the a priori algorithm for frequent item set mining. My name is Philippe Fournier-Viger, professor and founder of the Spmf Software. Okay, so let me give you some introduction first. There are a lot of stores, like retail stores, that collect some data about the customers, about what the people buy. For example, some big stores like Amazon will collect a lot of data about what the people are buying. Now, if we have a lot of data about what the people buy, what we call the customer transactions, we can analyze this data to understand the behavior of the customers. So, for example, we can analyze the shopping data and find that many people who buy the bread also buy the water together many times. So if we find something like this in the data, then maybe we can sell the bread with the water or give a discount to sell them together or do some marketing, because many people buy these items together. Okay, so of course this is just an example, but I want to say that analyzing the customer data is very useful. So why? For the marketing purposes, also to manage the inventory in a store, and also to manage the customer relationship. So in the field of data mining or data science, one important topic is how to discover patterns in database or associations. We want to discover some interesting relationships in the data. For example, there's a classical example. People say that they have analyzed the data of a store and found that people who buy the beer also buy the diapers. Okay, so why? In that story that we talk in data mining, there was some young daddy who go to the store to buy the diapers for their baby, and then they will also buy some beers at the same time. So apparently that while looking at the shopping data, some people found that people were buying the diapers and the beer together. Okay, so what I want to talk to you today is pattern mining. It is a fundamental data mining problems where we look at the data and we want to find some interesting associations between the values in the data. Something, water always appear with bread and so on. Okay. Mainly this problem was, this field was introduced by Agrawal in 1993. And then many extensions of this problem were proposed to discover all kinds of patterns, like in graphs, in sequences, in spatial data, and many other kinds of data. So today I want to talk to you about one specific problem in pattern mining. It is called the frequent item set mining. So frequent, what does it mean? It means we want to find something that appears many times in the data, like many people buy bread with milk or bread with water and so on. An item set, what does it mean? That means a set of items, for example, products, so like bread, water, orange, and so on. So we find some sets of items or values that appear many times in the database. That's what we want to do. Okay, so to introduce this problem, I want to first explain some definitions. I will use some examples to make this very easy to understand. Okay, so we suppose that we have a set of items in our database we call I. I is the set of item, and we have the items I1, I2, and so on. So for example, if we take again the example of shopping, the items could be pasta, lemon, bread, orange, and cake. These are products that different customers can buy in some store. So here, to make it simple, I will only use these 5 products in my example. But of course, in real life, there can be millions of products of different items. And in this presentation, I will talk to you about the example of shopping, but item set mining can be used in many other fields. Actually, the items are just symbols. We could use this to represent other data like text and so on. Okay. Now, we suppose that we have a database we call a transaction database. A transaction database, it is a set of many transactions, and where each transaction, T1 for example to T4, is a set of items. So for example, in my example here, I have 4 transactions, T1, T2, T3, and T4. These are the names of these transactions. In T1, there was a customer who bought the items pasta, lemon, bread, and orange. In transaction 2, another customer bought pasta and lemon. In transaction 3, some customer bought pasta, orange, and cake, and so on. So we have some data like this about transactions made by customers in the store. So each transaction has a unique identifier that is called the transaction ID. So for example, the transaction ID of T4 is 4. Okay, so this is very simple. The transaction ID of the first transaction is 1 because it is called T1. Okay. Now, as I said before, a transaction is a set of items, what we call an item set. What is important to know is that in a transaction like T1, there is no order. T1 means a customer bought pasta, lemon, bread, and orange. But there's no order. We just bought these items together, not before, after, and so on. There's no order here. And also, we don't know how many times pasta was bought. Do we buy 1 box or 2 boxes, and so on. So in this problem, there's no quantities, how many, okay. So, about the transaction database, you can also think about this as a binary matrix. So, this is the same as what I showed you before. It is another representation of the same data. So here in transaction 1, we have pasta, so we have 1, lemon 1, bread 1, orange 1, and 0 for cake. So 0 means to not buy, and 1 means we buy something, and so on. Okay, so what I show you here is the same as what I showed you before. It is just another way to represent the same thing. Okay, so if we have the set of items that I showed you before, pasta, lemon, bread, orange, and cake, these are the products that are sold in our store, for example. So now I want to talk to you about all the combinations of items that we can make. So for example, if we have 5 items, pasta, lemon, bread, orange, and cake, we can make 2 to the power of I minus 1 combination. So if we have 5 items, 2 to the power of 5 minus 1 equal 31 combination. So let me show you. Okay, we can have pasta, or lemon, or bread, or orange, or cake. But then also we can have pasta with lemon, pasta with bread, pasta with orange, pasta with cake, and then lemon with bread, lemon, orange, and so on. And then pasta, lemon, bread, orange, and cake. So all the combination of pasta, lemon, bread, orange, and cake, there are 31 subset of these combinations actually. So here in my example, only 31 combination is not a lot. But consider that in a real database, there are 1 million products. So the number of combination will be 2 to the power of 1 million minus 1. So that will make a lot of combination in real life. But here again, I use a simple example with only 5 products so I can explain it in a simple way. Okay, so I will not make the proof about this 2 to the power of I minus 1, but it is very easy to calculate this actually. Okay, so let's continue. Okay, so some more definition. We say that an item set is said to be of size k if it contains k items. So let me give you some example. If we have a set with only pasta, then we say it is an item set of size 1 because it contains 1 item. Lemon is also an item set of size 1. Bread, orange, and also cake. Now if we look at the item set of size 2, we have, for example, pasta, lemon, pasta and bread, pasta and orange, and so on. Okay, now I want to give you some more definition. Our goal is to find some sets of values that appear many times in a database. So we need to be able to measure the frequency, how many times some set of items appear in the database. So to do this, we define a measure that we call the support. Okay. So the support of an item set is the number of transactions that contain the item set. Okay, so if it is not clear, I will show you this with an example. For example, we have the set of item pasta and orange. So the support of pasta and orange is said to be 3. Why 3? Because pasta and orange appear together in 3 transactions of this database. Okay, so let's have a look. In transaction 1, we have pasta and orange. In transaction 3, we have pasta, orange. And in transaction 4, we have pasta and orange. So 1, 2, and 3 times. So that means pasta, orange as a support of 3. Okay, so this measure called the support is used to calculate the frequency, how many times something appears in the database. About the support, I want to explain something very quickly. Sometimes in some papers you will see that the support is a percentage instead, like 75%. So what does it mean? It means here we say pasta and orange has a support of 75% because it appears in 3 out of 4 transactions in the database. So if we want to calculate the absolute support, we count how many times pasta and orange appear together, so 3 times, divided by the number of transactions, 4. So the support is 75%. So this is just another way to define the support, but it is equivalent. Okay, so now I want to explain to you the problem of frequent item set mining. So in item set mining, we suppose we have a database like this, database of transactions, and that the user will set a parameter we call the minimum support or min sup. That means the minimum frequency. Okay. So the goal of frequent item set mining is to find all the frequent item set. That means the set of items or values that have a support at least equal to the minimum support, to this minimum. Okay. So I will show you this with an example. Okay. Let's say we have the same database I use as example, and then we set the minimum support to 2. That means we want to find all the sets of items that appears at least in 2 transactions of this database. So the result will be the following. You can see here. So here we say that lemon is a frequent item set because it appears at least twice in the database. So if you have a look at lemon, it appears once, twice, and 3 times. Okay, so it is at least 2 times. So it is a frequent item set. Let's look at some others. Lemon, pasta, orange. Lemon, lemon, pasta, orange 1 time. Lemon, pasta, orange 2 times. So it appears twice. It has a support of 2, at least 2. So it is a frequent item set. So having a database, we set the parameter, the minimum support, and we want to find all the frequent item set in this database. So this is the solution I show here, the result that we want to find. So as the user, we need to choose the value of the minimum support to find the frequent item set. If we choose the value, very high value, like 4, then we will only find a few frequent item set, because if we set min sup to 4, there are very few item set that appear at least 4 times. And if we set the minimum support to 0, then we will find everything will be frequent in our database. We'll find a lot of frequent item set, and it will take more time to find the result because everything will be frequent. So as the user, we need to set this parameter, and then some algorithm will find the frequent item sets for us. Okay, so why frequent item set mining is interesting? Because it has many applications. Here I just talk about shopping, but it can be used also for medical application, in chemistry, in biology, e-learning, and so on. So for example, in e-learning, the transactions and the items will not be about shopping, but it could be, for example, some transactions, one for each learner, and then the item could be the courses that the students took, for example. And we can find the frequent set of courses that the student will take. This is just an example, but actually there are many ways to apply this, not just for shopping. Okay, so if we want to find the frequent item sets in the database, there are several algorithms. The first one is called Apriori in 1993, very popular. Actually, it is the first one. It is not very fast, but it was the first, and then it has inspired so many algorithms after that. So, and it has introduced some very important ideas for this field. So I will talk to you about Apriori today. And after that, there was ECLAT, FP Growth, LCM, and others. And also many other extensions of the frequent item set mining problem. For example, to consider the profit, the money, the weight, the time, to find the rare item set, and many other things actually. Okay, so now I would like to talk to you about some algorithms to find the frequent item set. So before I explain one algorithm called Apriori, I want to talk to you about the naive, the simple way to solve this problem. Okay, so if we want to find the frequent item set in a database, the naive approach, the simple approach, will be to look at all the possibilities, like pasta orange, pasta orange bread, and so on, all the possibilities. So if there are n items, like 5, there are 2 to the power of 5 minus 1 item set. So we could take all these combinations and calculate the support and only keep the frequent item set. But there's a big problem with this. If we count the support of all the item set, if we have only 5 items, it is okay. Only 31 possibilities. But if we have 1 million items, then we need to look at 2 to the power of 1 million minus 1 possibilities. And then the algorithm will be very, very slow, maybe, depending on the parameter. So, and it will take a lot of time to read the database many times and calculate the frequency of all these items. So it will be inefficient because we need to do too many comparisons, and it will requires a lot of memory. Okay, so let me explain this in more details for our example. Here I show you the search space, all the possibilities for the item set mining problem. So here I use again the same example. In our database we have lemon, we call L, pasta, we call P, bread, B, orange, O, and cake, C. So here I show you all the possibilities. On top you can see the empty set, that means nothing, we buy nothing. Then lemon, or pasta, or bread, or orange, or cake. So this is the single items. Then we have 2 items together, LP, lemon pasta, or lemon bread, lemon orange, and so on. Then we have the 3 items, the item sets with 3 items, lemon pasta bread, lemon pasta orange, lemon pasta cake, and so on. Then we have 4 items, and then we have all the 5 items together. So these are all the possibilities. There are 32 possibilities, and if we don't count the empty set, there are 31. So if we use the naive approach, we will look at all the possibilities and count how many times they appear. It will take a lot of time. Okay, so this representation I use here, I just want to say it is called a Haas diagram. It is this kind of picture where we have each node is an item set, and there's a link between 2 item sets if one of them is a subset of another and contain 1 less item. So there will be a link between them and so on. Okay. Now, if we set the parameter minimum support to 2, here I show you the frequent item sets. So in yellow color, you can see all the frequent item set. So lemon, pasta, lemon orange, lemon pasta orange, and so on. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, plus the empty set if we count. So the goal in frequent item set mining, if the user set the minimum support to 2, we want to find all the frequent item set, the yellow item set in my picture. Okay. So here I want to show you the size of the search space. If we have only 1 item like A, then there's only 2 possibilities, the empty set and A. If we have 2 items, A and B, there are 4 possibilities, A, B, AB, or nothing. If we have A, B, C, there are about 8 possibilities. Nothing, A, B, C, A, B, A, C, B, C, A, B, C. Then if we have 4 items, it looks like this. 5 items, then 6 items. You can see the search space become very, very big, and so on. And if we have 1 million items, like in a real store, the search space will be huge. Okay, so we don't want to look at all the possibilities. So, how to find the frequent item set? We want to do something better. There are 2 challenges. First, we need to count the support of the item set in an efficient way. We don't want to spend time to count how many times all these item sets appear to find the frequent item set. And also, we want to reduce the search space. That means we don't want to look at all the possibilities. We want to find the frequent item set, but we don't want to look at all of them, all the infrequent item sets. Okay, so I hope this is clear. Okay, so now I will explain to you the first algorithm for this problem. It is called the Apriori algorithm, proposed in 1993 by Agrawal and Srikanth. Okay, I hope I pronounced the name properly. Okay, so Apriori is a famous algorithm. It is not the best algorithm in terms of performance, but it has inspired many other algorithms. It has been applied in many fields. It has been adapted for many other problems. So this algorithm, very, very popular. It has been explained in many, many books and so on. And before I explain the algorithm, I want to show you 2 important properties that have been proposed in this algorithm. Okay, so the first property, first I will give the definition, then I will show you with an example. It will become very clear. So what we call the a priori property, let's say that we have 2 sets of items, X and Y. Some set of items or products, X and Y. And we suppose that X is a subset of Y. So, for example, X could be pasta orange and Y could be pasta orange cake. Then, if we have this, the support of Y must be less than or equal to the support of X. So what does it mean? If X is a subset of Y, Y cannot appear more often than X. The support of Y cannot be more than that of X. So let me show you with an example. Here we have pasta. Pasta appears 4 times in the database. So we have pasta, 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 pasta. So the support of pasta is 4. Now if we look at another item set like pasta lemon, it appears 1, twice, and 3 times. So pasta lemon, the support is 3. So the a priori properties say that if you have an item set like pasta and a superset like pasta lemon, the support of the superset of pasta cannot appear more often than pasta here. So pasta lemon cannot appear more times than pasta. The support of pasta lemon cannot be more than 4. And of course it makes sense, because if pasta appears 4 times, for sure pasta with lemon cannot appear more often than pasta, because we add something else, okay? And the same thing, if we have pasta lemon orange cannot appear more often than pasta lemon. It cannot have a support more than 3. It must be 3 or less. So this a priori property also we say that is the same thing. Sometimes we say the support is anti-monotonic. That means the same thing. Okay. Okay, so I hope this is clear. I will continue. Now I will show you with some picture. So if we look at the picture here, what does it mean? Here on this picture, I show you the yellow item set or the frequent item set. So that means that if you have some sets of items like bread, B is not frequent, bread. So that means that all the supersets of B, like pasta bread, or lemon bread cake, or pasta bread orange, okay, all the superset of bread cannot be frequent, because if bread appear only one time and the minimum support is 2, anything with bread cannot be frequent. So let me show you this. If we know that bread is not frequent, we know that anything that will be made with bread, any item set with bread, cannot be frequent. So that means all the item sets with bread here in red, we don't need to look at them. Okay, so if we know that bread is not frequent, everything that contains bread, we don't need to count the support, because they cannot be the frequent item set. So this is a very important and very powerful property. If we know bread is not frequent, we avoid looking at all the red item sets in the database, so we can save a lot of time. Okay, so now there's a second property, property number 2. It is about the same property as property 1. It's just another way to say the same thing. Okay, so if we have an item set Y and another item set X that is a subset of Y, and X is infrequent, then Y must be infrequent. Okay, so let me show you this with an example to make this clear. If we have an item set like Y, like bread and lemon, and we find that a subset of Y, X, like bread, is not frequent, then of course bread and lemon cannot be frequent. So bread appear only one time, then of course bread with something else like lemon cannot appear more than one time, so it must be also infrequent. So as I said before, this is just another way to write the same property, property 1, but this one we call property 2. Okay, so if you have understand this, now I will explain to you the a priori algorithm, how it works. To explain a priori, I will use the same example to make it easy to understand. I will explain the algorithm directly using the example to make it simple. Okay. So what is the input? It is a parameter we call the minimum support and a transaction database. And what is the output? The output is all the frequent item sets. That means all the item sets that appear at least a minimum number of times. So for example, if we set the minimum support to 2 for our database, the result, I will show you how to find the frequent item set with a priori. Okay, now. So, if we set the minimum support to 2, the first step of the a priori algorithm is to scan the database to find the support of all the item sets of size 1. That means each item. So we read the database one time and we find that pasta appear 4 times, lemon 3 times, bread 1 time, orange 3 times, and cake 2 times. Now we continue with step 2. Step 2, we eliminate all the infrequent item set. So bread appear only once, so we don't need to keep bread, because as I said, everything that will contain bread cannot be a frequent item set. So here I have removed the bread. Now we have 4 items left: pasta, lemon, orange, and cake. So these are the frequent item set of size 1. So the a priori algorithm will output them. Now we will continue. Using the item set of size 1 that you can see here, we will try to look at the item sets of size 2 items. So this is step 3. We use the item set of size 1, the frequent items, and we combine them to obtain some item sets of size 2 that are candidates that maybe are frequent. We don't know yet, okay? So we take pasta, we combine with lemon. So pasta, lemon. Pasta with orange, that makes pasta orange. Pasta with cake, that makes pasta cake. Then lemon orange, then lemon with cake, and then orange with cake. So we combine all of these one by one together to get some candidates with 2 items. And here, what is important, all these candidates of size 2 are some item set that might be frequent. We don't know yet. But you can observe that we don't look at bread. So everything with bread we don't consider because we eliminated bread already. Now we will look at these candidates. We need to find the frequent item sets of size 2. So step 4. We eliminate the candidate of size 2 that have some infrequent subset, property 2. Here, so that means if we look at pasta, lemon, we look at the subset like pasta. Pasta is frequent, lemon is frequent. So we don't need to eliminate. We cannot apply the property 2. So we do nothing here, okay. Now, step 5. We have these candidates. We read the database to count the support. So we read the database and find that pasta lemon appear 3 times, pasta orange 3 times, pasta cake 2 times, lemon cake once, and so on. Now after we find this, we do step 6. We eliminate the infrequent candidate of size 2. So we eliminate lemon cake because it has a support of 1. It is not frequent. Now we eliminate this, okay? So I eliminate. Now so we have found the frequent item set of size 2. There are 1, 2, 3, 4, 5. So the algorithm, we output them to the user. Now we need to continue. We found the frequent item set of size 1 and 2 already. We need to find size 3 items together. So what we will do, step 7, we take the frequent item set of size 2 and we combine them to generate some candidate of size 3. So here we take pasta lemon, pasta orange, and we combine together to get pasta lemon orange. We take pasta orange, pasta cake, we combine together to get pasta orange cake. We take pasta lemon, pasta cake to get pasta lemon cake, and so on. So we take the frequent item set of size 2, combine them together to get some candidate of size 3. Okay, so it is to be noted that maybe you can combine some of them to get size 4, but here we only want to get size 3 because we'll do size 4 later, okay? Now only size 3, this is important. So now we apply the property 2. We eliminate the candidate of size 3 that have some subset of size 2 that is infrequent. So let's look at the first one, pasta, lemon, orange. We look at all the subsets of size 2. Pasta, lemon. Does it appear here? Yes. Pasta, orange. is it here? Yes. Lemon orange, is it here? Yes. So this one is maybe frequent, so we cannot eliminate. Now we look at the second one, pasta lemon cake. Is there some subset of size 2 that is infrequent? So pasta lemon is here, is okay. Pasta cake is here, is okay. Lemon cake, is it here? Lemon cake? No, it's not here. So we know that this item set cannot be frequent, so we eliminate. Now we do pasta orange cake. All the subsets are frequent, so it's okay. Now this one contains again lemon cake of size 2, and it is infrequent. We don't have lemon cake, so we can also eliminate this one. So after we do this, we have only 2 candidates of size 3. So now we'll scan the database to count the support. So this is step 9. We read the database and find the support of pasta lemon cake is 2 and pasta orange cake is 2. Okay, so all of them are frequent, so we output them to the user. So now we have the frequent item set of size 3. So we'll combine them together to generate some candidate of size 4 that might be frequent. So here we have pasta lemon orange cake. So we continue. Step 12. We apply property 2. We look at the subsets of size 3. All of them are frequent or not. So pasta lemon orange, is it frequent? Yes. Pasta lemon cake, is it frequent? No. So this one cannot be the frequent item set. So we don't need to scan the database. We eliminate this item set. We save some time. So now we eliminate this and we have nothing left. So we stop. And we found the final result. These are the frequent item set. Size 1, size 2, and size 3. So, what I explained to you is the a priori algorithm. Now you should understand the main idea already. Okay, so now I want to explain some technical details about this. If you want to do the programming, okay. So, one important detail, if you want to do programming, it is that if you combine different item sets, you can obtain the same candidate. So let me explain to you this idea. If you combine AB with AE, you will get ABE, of course. But if you combine BE with AE, you will also get ABE. So this is not good, because if you combine AB with AE, you get ABE, and BE with AE, you also get ABE. But if we do some algorithm, we don't want to look at ABE more than once. We don't want to generate ABE many times, to always look at this item set. So there's a special trick to avoid this problem. Let me explain to you the solution. The solution is to sort each item set by some order, like the alphabetical order, like ABC. So all the item sets are sorted by the order like ABC. And then we combine 2 item sets only if all items except the last one are the same. So if we have AB and AE, we can combine them because they are the same except the last one. So A is the same, but B and E are not the same, the last one. So we can combine them. But BE and AE, we cannot combine them because they are not the same except the last item. So the first item is not the same, so we cannot combine. And if we do this simple solution, we will make sure that we never generate the same item set twice. Okay, so maybe it is not so obvious, but it is true actually. I will not make the proof here. But if you want, you can do the proof about this, and you will find that it is always true. If you sort the items and you combine them, if all the items are the same except the last one, you will never generate the same item set twice. So this is very important if you do programming for this algorithm. Okay, so now the Apriori algorithm, is it a good algorithm? In my example with 5 items, I told you there are 31 possibilities. But if we use Apriori, we don't need to look at all of them. We only look at 18 item set in this example. So actually we save a lot of time because we don't look at all the combinations to find the results. So here for 31 possibilities is not a big difference. But if you add 1 million items, then maybe using Apriori it will make a very big difference. Okay, so the Apriori algorithm, we can say that it is a complete algorithm. That means it will always find all the frequent item set. It will not miss anything. It will find always the good solution. And also it is correct. It will correctly calculate the support of all the frequent item set. It will not output any item set that is not frequent. Okay, so here I will not do the proof. But if you want to do the proof, it is not so hard to do. And also you can have a look at the original paper about Apriori. Now I want to talk to you about the performance of Apriori. So if we want to evaluate such algorithm, we can think about a few things. How is the execution time? How much time it takes to find the solution? How much memory it uses? And how about the scalability? If we have a lot of data, will it be very fast or very slow? Okay. And also, we want to test the algorithm on different types of data. On the real data, on the fake data, on the data with the long transactions, with a few items, with many items, and so on. So if we want to evaluate such algorithm, we need to do some experiment. Okay, so here I show you some example of experiment. I implemented all these algorithms in Java as part of my software called Spmf, and I do some experiment on some database called chess. So here you can see Apriori, ECLAT, FP growth, and others. So this is the time, how many seconds, and this is the minimum support as a percentage. So here you see Apriori. It is actually very slow. It takes about 150 seconds when the minimum support is about 0.6. But you can see that some other algorithm like FP growth take maybe less than 1 second, when Apriori take about 100 seconds. So Apriori is not the best algorithm. There are some much better algorithm like FP growth. But Apriori is still much better than the naive approach. It's not a very bad algorithm, but it is not the best. Okay, so this is what I wanted to show you here about the performance. So in general, I want to talk to you more about the performance of Apriori. It depends on several factors. How we set the minimum support parameter. if we set the parameter low, the search space will become very big. We need to look at more possibilities, and it will take a lot of time, use more memory, and so on. And we find maybe more frequent item set, but also the number of items, the number of transactions, and the transaction length will influence the performance. So if there is more items, the transactions are longer, then the performance will decrease. It will take more time, more memory maybe. Okay, so there are a few problems about a priori. First, it can look at many candidates. Actually, it can look at some candidates that does not exist in the database. So for example, if we take AB, AC, we combine to make ABC, then maybe ABC does not exist in the database as a support of 0, and then a priori will spend some time to look at some item set that does not exist in the database. And also, a priori need to read the database many times to count the supports of all these candidates. So maybe it will spend a lot of time. Okay, so if you want to do programming, there are several optimizations you can make to make a priori faster. Okay, so here I just want to give you a few ideas about how to make a priori a little bit faster. Okay, so a first optimization, if you want to do programming, the first thing you should do about the items, if you have the items like pasta, you should not store this as a string. Okay, you should use integers like 1, 2, and 3. So instead of using pasta, orange, and bread, inside the program, you should use 1, 2, and 3. Because if you use integers, then like 1, 2, 3, it will use less memory than if you use a string. And also, it is faster to compare two integers than to compare two strings. So if you compare 1 and 2, it is only one operation in your computer to compare 1 and 2. But if you want to compare two strings like pasta and orange, it will take more time because you need to look at P and O, A and R, and so on to compare them. Okay, so this is the first optimization. Optimization number 2. Another trick. We can sort the database by the length of the transactions. So here I put all the transactions with 2 items, then 3 items, then 4 items, and so on. So the transactions is sorted by the size of the transactions. So now if we look at some item sets with 3 items, for example, we know that we don't need to look at all the transactions with 2 or 3 with 2 items or 1 items, because they are sorted by increasing length. We can save a lot of time when we scan the database. So this is another optimization. Optimization number 3. We can observe that in some database we have some identical transactions. They are the same. So we can merge all of them and replace them by 1, for example. So this could save also sometimes. If there are many transactions that are the same, we merge them and replace them by a single one. Okay, so here I don't have the example, but it's just some idea you can use. Idea number 4. When we calculate the support of some item set in some transactions, we can sort the items in the transactions according to some order, like the alphabetical order. And when we search for some items in the transactions, we can use the binary search to search more quickly. So if the transactions are very long, it will save maybe a little bit of time. So this is another maybe possible optimizations. And there are also other optimizations that we can use. Okay, so now I want to explain to you another optimization or another way to implement Apriori to do the programming. It is called Apriori TID. You can think that it is another algorithm, but actually it is Apriori, but just a little bit different. Okay. So the idea is the following. We will annotate each item set with the IDs of the transactions that contain it. And then we use the intersection operation to calculate the support of all the item sets without looking at the database. So let me show you this. Here we have the original database on top. We call an horizontal database. And then we convert this database to what you see at the bottom. We call a vertical database. So what you see on top and at the bottom is the same thing. It's like we take the database on top and we rotate the database. We change the perspective to get the one at the bottom. So at the bottom you see pasta appears in T1, T2, T3, T4. So if you look on top, pasta appear in T1, T2, T3, and T4. So pasta T1, T2, T3, T4. Lemon appear in T1 and T2. Lemon, here it should be, sorry, there's an error, T1, T2, T3. Okay, so lemon appear in T1, T2, T3. Bread appear only in T1 and so on. So these two tables are the same. So first we read the database and then we create this table you see at the bottom. Now if we use this table, we can quickly count the support of any item set without looking at the database. So for example, if I want to calculate the support of pasta, lemon together, I take the transaction of pasta and I do the intersection with the transaction of lemon, and it will give me the support of pasta, lemon. So pasta appear in T1, 2, 3, 4, intersection the transaction of lemon, T1, T2, T3, 4. So the intersection is T1, T2, T4. So that means 3 transactions. So the support of pasta, lemon is 3. So using this idea, we can calculate the support of all the items set in the database without always reading the database. So this version of Apriori we call Apriori TID, and sometimes it is faster than Apriori because we don't need to always read the database. Now we can improve this, make this better. There is another version of Apriori we call Apriori TID bitset. So it is the same idea except that we use the bit vectors instead of the list of IDs. So let me show you this. We take the database and then we use some bit vectors. So here for pasta we have 1, 1, 1, 1. It means that pasta appear in T1, T2, T3, T4. Now if you look at lemon, we have 1, 1, 0, 1. That means lemon appear in T1, T2, does not appear in T3, does not appear in T3, and appear in T4. So 1, 1, 0, 1. Bread, we have 1, 0, 0, 0. That means appear in T1 and does not appear in T2, T3, T4. So if we use this, it takes less space maybe, because we use the bit vectors. So all of this is only some bits. So depending on the database, it can take maybe a very small amount of memory. And now if we want to calculate the support of pasta with lemon, we do the logical operation of the vector of pasta 1 1 1 1 and the vector of lemon, and it gives you the vector of pasta lemon. So pasta lemon appear in T1, T2 and T4. So the support of pasta lemon is 3. So if we do this, we can also make a priori faster maybe. It depends on the database, of course. And maybe we save some memory because we use the bit vectors. So in conclusion, in this video, I show you, I explain to you the a priori algorithm, and I show you some optimization. I hope it was interesting. So if you want to try a priori, you want to use it in Java, you can use my open source software called Spmf, and you will get the source code of a priori and also of many other algorithms for item set mining. So if you want to use it, one moment. So here I show you the Spmf software. You can download from the website. You can find in Google or other search engine. So if you use the software, first you click a priori. I want to use a priori. Then I will choose some database. I will use some database called Context Pasquier 99. So this is the input file. Then I want to create some output file. Okay, so I will call this output.txt. So the output will be a text file. And I said the minimum support will be 0.4. And then if I want to run the algorithm, I will click run here. Just before I run the algorithm, I want to show you the file. So the input file looks like this. It is 5 transactions, so line 1, 2, 3, 4, 5. And the first transaction is the item 1, 3, and 4. So like pasta, orange, and cake, for example. The second transactions is 2, 3, and 5. So the numbers here, 1, 2, 3, 4, 5, is the name of the items. And here I have 5 transactions. So if I click run, I click run on the software, and I see the result. Here I have all the frequent item set with the support. So I see the item set 2, 3, 5, like pasta, cake, orange, and so on, for example, as a support of 3 and so on. So using the software, you can use a priori, but you also have many other algorithms, a priori TID, TID bit set, you have FP growth, ECLAT, and many others to find the patterns in the database. So that's all for my presentation. I hope you enjoyed this. Thank you for listening.